This is the second half of 2 lectures on finite elements. The warning I gave right at the beginning was it's quite complicated. Please use packages where it's all been all the horrible details have been handled for you. The problems of generating a grid and calculating the matrix elements over a grid, and then getting a solution, where there's not a particularly good fast Poisson problem, and then representing the answer in nice graphical form. Let someone else do all the work for you. The first lecture tomorrow morning, I'll give a quick demonstration of one package that does all this, trying to show that despite manuals which are over 400 pages long, in 1 or 2 sheets of A4, I can give you enough of a hint to be able to use the package. Okay, so the first part, the first ideas we had this morning about finite elements is that there are 2 ideas that get combined. One is the representation. We move away from finite differences where the unknown function is represented by some spot values on a grid to we're representing the unknown function by a sum of continuous functions, so we can work out the value of the unknown function anywhere, and we use continuous functions, basis functions phi I, and multiply those basis functions by parameters fi. Sometimes those parameters are the values of the function at some point, but sometimes they're the value of a derivative somewhere or something totally different. So it's a sum of some parameters fi times some simple basis functions. Rather, for example, simplest useful one is a linear function over a triangle. And this means the basis functions tend to be non-zero only in a few elements in a few triangles. So that's a representation of the unknowns, and then we plug that representation into a variational statement. Instead of solving a partial differential equation, I minimize an integral. And I've just rubbed out the proof that there is a connection between the 2. So if we substitute in that representation into the integral and minimize by over what are the best values of the parameters that minimize the integral is a quadratic in the values of the parameters. When we take a derivative with respect to the values of the parameters, we end up with a linear function of the parameters, and we end up with this ax equals b, kf equals r, as the normal letters used to solve for our Poisson problem, where k is a matrix, the stiffness matrix, and it's an integral of the product of gradients of 2 basis functions, and the forcing of the original problem, rho, has come down to Ri, a product of the forcing rho with a basis function. Okay, so I had last time tackled this Poisson problem in 1 dimension. Let's do it in 2 dimensions and see what we get. So I'm thinking of a linear basis functions over triangles. Sometimes the elements are not triangles, but not very often. And the linear basis function is the simplest, that's useful. So it vanishes at 2 vertices and is equal to 1 at the 3rd vertex, and therefore the gradient of the basis function is 1 upon the height of the triangle, the distance from the vertex where it's 1 to the baseline. So here is the triangle. the vertex where it's going to be 1 and the other 2 vertices, I've got an altitude and a baseline. I'm sorry you can't see, there's a 1, 2, 3 here. And the integral for the stiffness function, the K1, which is the basis function 1 times gradient of the basis function 1 dotted with the gradient of basis function 1, that's going to be 1 upon h squared, constant, and then when I integrate it's the area of the triangle. These packages do all this for you, but this is what's going on. And if I wanted the matrix element K1, 2, that is going to be the dot product of gradient phi 1, gradient phi 2. This is 1 upon h1, this is 1 upon h2, but the vectors are in different directions. One is perpendicular to the one baseline, one's perpendicular to another baseline, and the angle between them is the angle there. So it's the cosine of that included angle. So therefore that matrix element is doing the area integral is the area, cosine, and h1, h2, and because they're pointing in opposite directions, there's a negative sign. Right. Now I can do a bit of geometry. That's the altitude from the first vertex down to the base is equal to one of the two lengths of the adjacent side, length 2, and cosine and sine of the included angle. Or I can do the altitude in the second direction is the symmetric version, and then the area is the base, say length 1, or say length 1 times h1, the altitude 1, and that is therefore a half the two lengths, length 1 and length 2, the sine of the angle in between. So if you substitute all those little formulas in, you find that the stiffness element K1, 2, that's what we found on the previous one, but with these is minus the cotangent of the third angle. So for element 1, 2 is angle 3. And because there's another expression on the triangle that the base is equal to a contribution from one side and the other side, the matrix element 1, 1 ends up being a half of cotangent angle 3 and cotangent angle 2. So 1, 1 involves the two other angles. So it just depends on the cotangents of those three angles to work out the matrix elements 1, 1 and 1, 2 and 1, 3. Yes, it would help a lot, wouldn't it? Yes. The one triangle, it shouldn't be an equilateral triangle like that one. So I'm staring very carefully. So this is 1, 2, 3. And this would be altitude 1. And we have, this is angle 3. And there is, do we have colors? There'll be altitude 3 there. That's altitude 3. Never mind. So the K1, 3 is the integral of phi 1, phi 3. This is 1 upon h1. This is 1 upon h3. And the angle between them, between that vector and that vector, is actually theta. And I form the dot product. I get a cos theta 3. Okay? And then I, on the next transparency, have done some algebra. The height 1 is the length of 2 times the sine of 3. Height 1 is this length of 2 times the sine of angle 3. This is angle 3 is down at vertex 3. And length 2 is opposite vertex 3. Sorry, length 2 is opposite vertex 2. So which, sorry? Yes. Is that wrong? Oh, up here. Okay. Thank you. That should be a 2 there. Yeah, I'm sorry, I drew the wrong orange altitude. I should have drawn altitude 2 to correspond with the transparency. Do you want me to start again and put H2 in rather than H? So H2 is the same as H1, but with the numbers moved around. The area is length 1, that's this length here times the sine of the angle in between, and a factor of a half. And then finally, this length 1 here is a contribution of this bit and this bit. So this is H1, the cotangent of angle 2, plus H1 times the cotangent of angle 3 will get me this bit plus this bit is L1. And I want those various little expressions in order to end up with the simplifications that K12 just involves the cotangent of angle 3, and K11 involves the cotangent of angles 2 and 3. Okay, so I can get those simplified formula with a little bit of elementary high school trigonometry. Do we agree it's a high school sort of? It's not university level, sure. Okay, now it's interesting that quite obviously if we add up what K11, K12 and K13, they add up to 0. So K12 involves the cotangent, so it's minus and a plus half cotangent, and you can see that by symmetry K13 will be the cotangent of angle 2, and that with a minus a half and a plus half, it all adds up to 0. So we only have to work out 2 of them, the off-diagonal ones, and you get K11 for free as being the negative sum of the other 2. Okay, and there's a reason for that, and that is because phi 1, which is linear and is 0 at 2 points and 1 at 1, phi 2, which is 1 at the vertex 2, and phi 3, which is 1 at vertex 3. If we add those 3 together, we get a function which is linear, because we're adding 3 linear functions, which is at 1 at each of the vertices, which is commonly known as a constant, 1. So the gradient of a constant 1 is 0, and therefore this dot product is 0, but the integral of the first term with the prefactor is K11, and then it's K12, and then it's K13. And therefore, they will have to add up to 0. And this is what's going to give us a conservation principle. Okay, so we were looking at one triangle, But of course, each vertex gets contributions from from 6 triangles. I've put a rather simple grid so I can do all the calculations of all the angles. The angles are either 90 degrees or 45, so I happen to know the cotangents of those angles. So I think I have to, it says look at triangle 1, 2, 3. You have no idea what triangle 1, 2, 3 is, have you? So made big. I want a big square. I've got that wrong, probably. Yes, we don't want that one. Want that one. And we don't want this one. Right. 1, 2, 3. So this is 1, 2, 3. And the odds are it keeps going round. Right. 4, 5, 6, 7, 8, 9. Have I gone wrong somewhere? 1, 2. I've got 5. I have not labelled them all. Okay. So it turns out this triangle is not connected with that point, so I'm not interested in it. I'm going to work out what the contributions from all the triangles for the K for that point are. So I'm not interested in that point, so we can keep going at 5, 6, and 7. And I'm not interested in that point, because that triangle's not connected to that. Right. Very good. So for triangle 1, 2, 3, so I'm going to look at this triangle here. And I'm interested in the contribution to K12 from this triangle, and it involves angle 3. Angle 3 is 45 degrees. Cotangent of 45 degrees is 1. So I'm going to get a contribution to K12 of -1/2. Do I believe that? Yep. I also want to know K13, the contribution that I get. So K13 involves the cotangent of the angle opposite. Cotangent of 90 degrees is 0. And then the contribution to K11 is equal to minus the sum of those, no new one to work out, is 1/2. Okay, so that's for the first triangle. And there is another triangle just like that. But there's a different sort of triangle with 90 degrees at the vertex. So we have to look at this type, that triangle, triangle 1, 2, 7. And there we're going to get a contribution to K12, which is the cotangent of the angle opposite. And that is, again, 45 degrees. So we get a contribution of -1/2. K13, there's nothing to come in. So we actually have to have a new line because we've got a new point. K17. 17 involves the angle opposite, which is 90 degrees, which the cotangent is 1. So this is -1. And then K11, well, what we do is is 0. Come on. Do I believe that? Wait a minute. What does the transparency say? 1. Okay. Right. Okay. For the orange triangle, 1, 2 involves the angle opposite, which is 45 degrees, so we get a half. For 1, 7, it involves the angle opposite, which is 45 degrees, so I get minus a half. And then for 1, 1, we get the negative sum of those, which is to add 1 more. Okay? Right. Now, if we go, now I know how to do 2 types of triangles, a 45-degree triangle and a 90-degree triangle. There's a 45 degree, a 45 degree, a 90 degree, and a 45 degree. And so when I add everything up, what do I get? Well, the important one is K11. I get 1 plus 1, and then I have 1, 2, 3, 4 halves. So when I've got everything else, adding all, I get K11 is equal to 4. The K12, I had a contribution from, so 1, 2 is in 2 triangles, and both triangles give me a half, minus a half. So K12 has a minus 1. And the same things happen there for K17, K16, no, K16 actually gives me a 0. K15 and K14. And as it says there, K13, the contribution is 0. So that one is 0, equally 16 is a 0. Okay. This is the sort of bookkeeping that the packages do for you. And we're only doing linear approximations. They will deal with quadratic ones and cubic ones. And it could be much worse. Okay, when it comes to working out the forcing for this point here, there are, as you can see, 6 triangles that contribute. So I have to know what is the area of those 6 triangles. And I've got linear functions. I have to integrate a linear function, say, by a constant. So integrating linear functions over those 6 triangles, the end of the is to get a third of the area. And so if we put everything together for this very special simple grid where it's easy for me to calculate things with linear functions, basis functions over those triangles, I end up with a problem which is exactly the same as the finite difference problem. So the finite elements are given the finite difference problem for the values of the vertices. So that's nice. Okay, so it's not done anything wrong. Okay, so this is the programming challenge that on a general unstructured grid, you need a list of vertices. So there are at point P, its coordinates are XP and YP. And there may be 500 of these, maybe 10,000. And then you need a list of triangles. And in particular, for each triangle, you have to know which of the 3 vertices. You need the inverse thing, that given a point, which triangles am I in? So you need these lists. Actually, there's a way of handling it by just listing the edges. Okay, and you also need an ability to search which triangle I'm in. If I tell you I'm at 0.5, 0.5, which triangle am I in, please? So you need a search procedure to find out when you're inside a triangle. Okay. And with all that, you can assemble, as I've done here, the contributions from the different triangles to the stiffness matrix, depending on your basis functions, whether they're linear basis functions or constant or quadratic. Okay. So the Poisson problem has a variational principle, which I'd sketch the proof on the board. Unfortunately, there isn't a variational version for the Navier-Stokes equation. There is a variational statement of a sort for the Euler equation with no friction. There's a variational statement for the Stokes equations called the minimum dissipation theorem. But for the Navier-Stokes equations, there is not a variational principle. So you get variational principles in physics if there is a quantity called action, which has dimensions of energy times time. You can say the variation in energy action is maximized, or action is normally minimized by the physics. Your governing equation of the physics in many types of physics can be written as you're minimizing the action. Action, okay. We teach mechanics in terms of momentum, and that's how I think. There are other things like energy, which are useful information, which the chemists tend always to use. The quantum mechanics have Planck's constant. Planck's constant is the same as angular momentum in dimensions, and Planck's constant has dimensions of action. And quantum mechanics would be so much easier if we first taught Newtonian mechanics in terms of action. You'd find quantum mechanics much easier. That's nothing to do with this lecture course. Right, so in general, you have a nonlinear partial differential equations, for example, our fluid flow, which varies in position and time, and you have a nonlinear equation with some forcing. It's nice to think about forcing, although sometimes we don't have force. But suppose there's gravity acting or magnetic forces or something like that. So this is du by dt plus u dot grad u minus grad plus grad p minus mu del squared u is equal to forcing, like gravity. That's a symbolic way of writing the nonlinear equation. What we do is we substitute into that governing equation, governing partial differential equation, a finite element representation. So we will have basis functions that depend on position multiplied by some parameters, and now we've got a time-dependent problem, so the parameters are going to change in time, and we want a question for us to solve is how do the parameters change in time? And we're going to do that, but just before we do that, I have to suggest there might be a dot product in a product which we can define between two basis functions or two functions of position as being an integral of the product over the whole domain. So this is just like dot products of vectors. Yes, that's okay with you. Good, good. It's just to explain the next line is what we do is we take the residual, so we take f away from this, and we should get 0. Of course, we don't get 0 numerically, but what we ask is that this residual has to be orthogonal. So OG is my way of saying orthogonal. It has no, okay, orthogonal. So it's saying, please, the residual has no component in the direction of not just one basis function, but all the basis functions. There's no way we can satisfy the governing equation in more directions than we're using, and we have a finite element with a finite number of basis functions. So please can the residual be 0 in all the directions I can look. So that is called a Galerkin formulation, and it's not quite as good as a variational formulation. And we call this Galerkin formulation that we're going to satisfy the governing equations numerically in this term of getting rid of the residual, a weak formulation. As I said before, we will use linear variations where the governing equation has got del squared, two derivatives. So what the pure mathematicians have to prove is that firstly, this weak formulation has a solution. Can you find values of the parameters such that this is true? When you've found a solution, first part. Second part is to show that as you increase the resolution, you tend to a limit. It doesn't just change randomly and not go anywhere. It has to go to a limit function. Thirdly, you have to prove the limit function is nice. That's when this curve, we're making linear approximations to, you get higher and higher resolution of, you get a higher resolution, more points on the linear approximation. It looks more and more like this curve. So you have to show the limit is a nice smooth function. It doesn't suddenly have discontinuities and weird delta functions and horrible things like that, which it quite could. If you take the limit of linear functions, you can get delta functions out of them. So we mustn't have that. And then finally, the fourth thing is, having proved there's a regular limit, does that regular limit satisfy the governing equation? It's quite easy to trend to a nice limit which doesn't satisfy, with all the terms satisfy something, but the limit doesn't satisfy something. Okay, so that's a major challenge for pure mathematicians. And because it's a major challenge for them, we say this is a weak formulation. We're not quite asking the solution to satisfy the governing equation, we're asking it to satisfy something else. And we know as applied mathematicians, as a physicists or engineers, that it'll work. So we do it. Okay, now there is this conservation property and it's automatic. This formulation asking for the residue to have no component in all of the base directions of all of the basis functions. And that comes from, if you sum over all the basis functions, on the whole you end up with the constant function. It's not always exactly true. Sometimes you have to throw away some of the basis function. But you should normally be able to find a sum of out of all the possible basis functions, which is the constant function 1, and then if you put all the basis functions you used in there into there, and then add them up, it's only a finite number, if you add them up, you've effectively put 1 in there, and 1 there, if you put 1 in there, you're saying that the integral of the governing equation is equal to the integral of the forcing. So that's the global conservation. Falls out automatically when you use finite elements. And that's the proof that it does. How are we doing? We have to go a bit faster probably. So I'm now going to the diffusion equation, which is a bit of the Navier-Stokes. We'll get to the full Navier-Stokes later. We have used this Galerking approach. So I've actually not got del squared on the left-hand side. Well, I've taken it onto the left-hand side as minus del squared. So is that right? Yeah, that's right. And then I've multiplied by phi j, and then I've done an integration by parts. So it originally was an integral of del squared u times phi j, but then I've taken one of the derivatives from del squared off u and put it on phi j. So that permits me a weak formulation. And then we substitute our finite element representation in as some amplitudes, which are going to be a function of time, times the basis functions, and I get, okay, so I then get this equation for how the amplitudes are going to change in time. Involves our stiffness function times the amplitudes that we've covered before, and there's a new matrix which is called the mass matrix in the area, as being the integral of the phi I times phi j over the whole domain. So that's what's happened to the diffusion equation. It's become this mu dot equals minus ku. So quickly, in one dimension, this diffusion equation, if I have linear elements equally spaced, the we had what the stiffness matrix was earlier. The mass matrix is 2/3 and 2/3 for the if I equals j, and 1/3 if j is one different from I, and 0 if the elements are not adjacent to one another. And hence the governing equation becomes, this is essentially 1 upon h squared if I take the h onto the other side. U dot is equal to the standard finite difference version of del squared. And it's not u dot, but it's 2/3 plus 1/6 of the things either side, which actually makes it a little more accurate. It is this sort of compact, higher order accuracy activity going on there. And unfortunately, I don't get what ui dot is. I get a linear equation involving, it's a triangle, I plus 1 and I minus 1. That's a triangular matrix, and a tri-diagonal matrix, and so they're very cheap to invert, as it says there. Okay. So this finite element formulation was a finite element in space, and it's delivered me what's called a semi-discretized, it's also, that is called the method of lines, that I end up with u dot, the parameter u dot, is equal to something from the space variation, and you've still got to come up with a numerical method of solving u dot equals something to do with u. And I recommend, here I've just written out what a first order forward time stepping method would be, as that seems to be as accurate you need be. So use some finite differencing method to do your time stepping, and finite elements to do your space representation. You should never, and there are people who have done this, you should never use finite elements to think about the time activity. You just use finite differences, or where there are sophisticated versions. It's a horrible mess if you use finite elements. It's just wrong. Okay. Okay, so this is in one dimension, and it says on the special grid, I get these matrix elements. Okay, this is that triangle bit here. This is true. This is in 2 dimensions, and what we get is this Laplacian, as we had in the Poisson problem before, just a minute ago, and then instead of u dot at the key point 1, we get 1/2 from there and 1/2 from all the neighboring points, and equally from all the neighboring points. So then solving what is u1, and its version extended to the whole domain, given what u1 plus all these bits are, is a little awkward inversion problem you've got to go through, as well as working out the Laplacian there. So we have a finite element representation. So we represent the unknown velocity field as amplitudes which are varying in time times basis functions. And there are 2 subscripts going on here. There's the subscript for x, y, z, 3 components of velocity, and the subscript I for the basis function. Sorry about that. I'm just ignoring that difficulty by writing a vector here for the x, y components, and this is the ith vector. This is the unknown amplitude times the basis function, and it's very important that for the pressure you use a different set of basis functions. So typically you would use quadratic functions for the velocity and linear functions for the pressure. Because if you think of your governing equation, you've got del squared u, which if u is quadratic, del squared u is a constant, is equal to grad p, so p ought to be linear. So we're dealing with the same order of magnitude polynomials. And then the Galerkin formulation is to say that the residue in the equation, I brought the right-hand side terms of the Navier-Stokes onto the left-hand side, have no component in all of the directions phi j. That's the momentum equation and the incompressibility condition, I'm asking, it's div u equals 0, divergence of u is 0, so I brought 0 onto the right-hand side. So the residual is just div u. Has no components in the directions of the psi's associated with the pressure. So we substitute in that finite element representation into those two Galerking approximations, weak formulations, do a bit of integration by parts, and we end up with our mass matrix as defined before, our stiffness matrix as defined by before. There are two new terms come in. There's Q for the u dot grad term, and you can see here it is a phi I grad phi j, that's a u dot grad u, and then in the direction, okay, actually I put the j, it doesn't matter. Yes, okay. I understand what I've done. And then the pressure gradient involves the phi's and the psi's. So we would put in pressure as psi's, a sum of psi's, and we make a dot product with the scalar product with the phi i's, phi for the momentum equation and psi for the pressure, so we get this term. And down in the incompressibility, it's the other way around, we're putting phi's with the u's, so we have grad phi, and we're taking the component in the direction of psi, so we have psi for the equation. So it's that. And they're the same thing with a minus sign, because you just integrate by parts. Okay, so that is the matrix version of the finite element version of the Navier-Stokes equations. And then you need to have some method of time integration, and I'm using first order integration in time, and you have to do a split time method to get to the pressure. So you make a first half step, ignoring the pressure. You take the governing equation and just switch the pressure terms off and go from un to u star. And then you ask, what pressures do I have to add to go from star to the final result, n plus 1, such that at the new times level, I satisfy div un plus 1 is 0. So div un plus 1 is this B matrix times un plus 1 is 0. Okay? So that's what you'd like to do. And then you get caught out because things go wrong. So one thing can go wrong is that the velocities get locked in by the boundary conditions if you have u equals 0 on the boundary, and we've got some internal forcing that's making the flow happen. The boundary conditions can actually force u to be equal to 0 in finite elements everywhere. So I'll show how that happens. If you have a linear representation of the velocity, so if you have basis functions for the velocity which are linear, it won't work, and pressure is constant, one derivative. So our incompressibility condition is to ask that div u has no components in the direction of all of the basis functions for the pressure. The basis functions for the pressures are constant. So this is asking for each triangle div u to be 0. The integral of div u to be 0. So that tells me the integral of the divergence of u equals 0 over triangle is the integral around the boundary of the triangle. There's no normal flow. So we'd like it's pretty obvious we'd like to have that, but if you ask for that, you get a problem. I've got one of my triangles. Okay, can you see the color? There's a blue color and a red color. That's all, you don't have to see the other bits. Okay, on the red triangle, which happens to have labels 1, the flow in here across this boundary, I'm trying to work out what this condition is going to be for a triangle. So what is the inflow and outflow into a triangle? And I'm on red triangle. There is a flow over the bottom edge, which is whatever h is here, and so the velocity, the vertical velocity is 0 here, and is some value at this point, which I've called v5, the velocity, vertical velocity at 0.5, and there's a linear variation between v5 and 0. What is the inflow? Well, it's a half of, it's the average of 0 and v5 times that length, that I'm calling h. That's the inflow of the bottom boundary. What's the inflow out of the angled side boundary? Here, well, this is going to be h times the square root of 2b, and is the length. And I've got a component upwards, which is going to be linearly varies between 0 and v5 here. So that's going to be, well, the normal component of that is actually that vertical velocity resolved normal, 1 upon square root of 2. So it's going to be a half of v5 divided by the square root of 2 to resolve it round, times h times the square root of 2. So it's a half h times v5, plus, of course, there's a horizontal velocity, u5 here, and there's going to be a flow outwards, which is going to be a half h u5. The half being because of the linear variation and resolving, which divide to a normal component, which is 1 upon the square root of 2, multiplied by an h times the square root of 2. Okay, so we know what comes in, a half v5, and what goes out is a half u5 plus v5. If there's no net flow, you've just concluded that u5 is 0. You can only satisfy the incompressibility condition. Given the no slip, I'm saying this is the outer boundary and there's no velocity on the outer boundary there. I've deduced there's no vertical velocity there. If I look at the blue triangle, it's just a matter of sort of a mirror symmetry around 45 degrees, and you'll make the deduction that v5 is 0. So using this no net flow into a triangle, plus it vanishes on two of all components of velocity vanish at 2 points of the triangle because it's a no-slip boundary condition. I've deduced that the velocity, both components of velocity vanish at this interior point. I've not talked about the momentum equation, and now I'm going to go on for the incompressibility for the next block, where I've got naught, naught, and now naught. I've just deduced naught, so I get naught there. And equally, for this one here, I've got naught, naught, and naught, so I deduce naught there. So just applying the incompressibility condition, I've deduced that the flow vanishes everywhere. Yes, this is bad, isn't it?
So if you bring it for the H4, 5, 4 is 0 and 5 is V5, and so you take half times H times V5.
Yes, if you want the integral along the boundary and you've got one value there and one value there, you want the average value, because they're linear variations, times the length. Any more questions? Okay, our big problem is linear variation in the velocity. That is one cause, and you can get out of it without not having that. The other problem is that it all looked very satisfactory when we were looking at one triangle. We have three vertices. Each vertex has got a u and a v. So we have 3 u variables, 3 v variables, and one pressure, because it's constant pressure. So that's a nice thing to have, is not so many variables for pressure as for velocity. Unfortunately, if you looked at I've just written it out here for a 3x4 grid, and work around carefully, you only have unknown velocities at 6 points, and you have 24 pressures. So locally at one triangle, it was good. But globally, when you put all the triangles together, you find that there's far too many pressures, which are and the pressures are the things that are all about satisfying div u is 0. So the pressures are controlling the velocity field through incompressibility and not giving the momentum equation a chance to do anything. So we need to create more, if we are going to have constant pressures, we need to create more velocity fields. And one thing to do is to immediately give a u and a v to every triangle by using a bubble function. That is a function that vanishes at the vertices and is non-zero in the middle of the vertex, in the middle of the triangle. So then it would be safe. There wouldn't be no problem. We wouldn't get that problem. And then there is another issue which we came across in one of the poor algorithms of using of the primitive variable formulation. There are finite elements suffer from spurious pressure modes. So think of the case when we have a pressure is linearly varying and it is plus in the middle, and at all the adjacent modes it is negative. So this is a mode which has this alternating signs across the grid. It's a spurious pressure field. And you think about what in the finite element formulation is going to happen in the momentum equation. And roughly speaking, in the momentum equation, it works out the pressure gradient from those 2 points either side. So for the momentum equation for this point in the middle, we consider the difference in the pressure between the two sides, the difference between air, and there's a bit of a contribution also from those two. But you can see this is plus, this is minus, this is minus. There's no pressure gradient from those 2 points. So that pressure mode won't contribute to the momentum equation. And that is because if you remember my finite element contribution, there was a new matrix B that came in, which was the integral of gradient of phi and a gradient of psi, this cross term. It means that this matrix has some eigen solutions, eigenvectors. So these eigenvectors don't get constrained, don't make a contribution to the momentum equation, and end up with spurious plus minuses across the whole field. Now, in finite differences, I made this trick of going to a staggered grid, and they all went away. The sad news is in finite elements, there isn't an equivalent. There's no move like a staggered grid. So, I'll come back to that remark. What people do is you cheat. Instead of satisfying div u equals 0, you say div u equals del squared p. Now these spurious modes, which go plus minus, they have very high gradients. So del squared of them is very big, and this equation really says go away, suppresses these high modes, the spurious modes. And it makes, if you choose the right quantity there, saying div u equals not del squared p, but a constant times del squared p, you don't do too much harm to the nice modes, and you only get rid of the spurious modes. And it's well known, for reasons which are not at all clear to anyone, that the best value for the constant is the grid size squared h squared times 1/40th. So 1/40th h squared times del squared p, you put that into your governing equations and everyone's happy. Okay. So it's called a pressure penalty, and you'll see that in the tomorrow. I have to introduce this term. Okay. So the weak formulation of this equation is, this is the divergence of u, and then this is this del squared p term here. Okay, so there's just one other thing, just a couple of other random things to say. Remember, in finite differencing, we worried about upstream influence to get u dot grad u right. So there is something called Petrov-Galerkin, where you fiddle with the basis functions to end up doing a bit of upstream influencing. They do a bit, therefore a bit good. They also introduce a lot of cross-stream diffusion. So it's not only upstream influence, but you're spreading information across streams in finite elements quite badly. Finite elements were good, designed originally for elliptic problems, Poisson problems, and as I said, they're pretty bad on hyperbolic problems, like u dot grad u. And then another idea that I use, I am interested in viscoelastic flows. This is actually the flow, a free surface flow of a granular column collapsing. You take it's a very nice experiment. Take a cylinder, make it out of paper, open at both ends, hold it on the table, fill the cylinder with sand, and then lift the cylinder up, and the sand spreads out. How far does it go? Well, the answer is the square root of the product of the radius and the height. That no one knows why. So people have done, I've written papers on this and I still don't understand why. I've done numerical simulations, and I've done particle-particle simulations, 10,000 particles numerically of sand doing this, and it doesn't. And I've done a certain continuum equation version of it. And so what there is here, there's a purple initial grid, and then there's a blue grid, a green grid, and finally a triangle grid, and I'm moving the grid with the flow. So I have a Lagrangian description. My grid, my mesh for my finite elements is moving with the flow, so that's called Lagrangian finite elements. And that's the way to deal with the hyperbolic equation, because in viscoelastic flow, we have a hyperbolic equation for the elastic stress. And you mustn't do any cross-stream diffusion. And there's actually another benefit, which I could explain to anyone who understands viscoelastic flows, that this moving with the flow is good for you, for that equation. There is a little hiccup that the elements get quite distorted. They started as nice triangles, and they ended up with rather stretched triangles. And there is a trick, if you should regrid. That costs a lot of money, generating a grid. So from time to time, you should regrid to avoid all these stretched out triangles. And there is a very nice trick that we use, which is swapping diagonals. So if you had one triangle and another triangle, and they're quite long, thin triangles, what you can do is to rub that out and replace it like that. And you get two triangles which are not long and thin. And that's a rather easy thing to do. And your time stepping, you visit every triangle in your time stepping, and you can say, would it be a good idea to swap diagonals with my neighbor? And if you do it every time step, it does the regridding for you quite well. However, keeping the angles nice and not long and thin is trying to maintain a Delaunay triangulation, and it turns out Delaunay triangulations can have unavoidable long, thin slithers, and it's worse in 3 dimensions. So it may be you don't want to do Delaunay triangulations with given points. You may actually want to move your points around, which is a regridding, to get a better mesh. Okay, so there are issues like that going on beyond what I'm talking about. Okay. And there's ALE, which is a nice combination between L Lagrangian and E Eulerian, but I don't like it. Fine. Okay. Does anyone have a question? I don't think this figure came out on your... That's because it was a .ps file and not a .eps file, and the tech didn't like it, ignored it. So I had to do there's a P2, a PS2, number 2 EPS converter, and it immediately works. Yes? Yes, it is. You're putting U is equal to a sum of these U i's, phi i's, into du by dt times a phi j is equal to, and then plus other phi j is equal to 0. This is the governing equation, and this is projecting in the direction of phi j. And if you put that into there, you're going to get a ui dot phi I, and then a phi j, and we're integrating over it. And that is ui dot times the mass. So it's mass with inverted commas. It's in other words, it's the word that this industry uses. It's slightly related to rho mass, real mass, physical mass, but it's not physical mass. If you were trying to think it was physical mass, that's not helpful. Yes.
So is it related to the mapping matrix actually? If the concentration changes with respect to that every point, it will be formulated by using some of the matrix actually. That is related to that mass matrix.
It's not a real mass. Okay. So, I think you were saying there's some
changes.
But I don't have concentration. This is pure Navier-Stokes. So I agree there are interesting cases where the concentration of salt changes the density of seawater, and you'd like to know about that, and that mass inertia comes into your governing equation. That's not, I'm not talking about that physics at all. So it's mass with inverted commas, and it's stiffness with inverted commas. This is a word used by the industry. Yeah, it's weak formulation. Yeah. Yes. Finite elements has to be. So it's a Galerkin, because in the viscoelastic flow and in my granular flow there is not a variational principle. So variational principles are Galerkin, but Galerkin are not variational. Variational has a special property that it is truly minimizing some action, some quantity, minimizing dissipation in Stokes flow. And there are other governing equations where there's not a quantity that is minimized. Okay, am I going to turn the sound off so you can't ask any more questions? Done.